let's finish off with, as promised, the long-delayed proof that the derivative of e to the x is e to the x. At this point, it is really simple and a mere application of everything we've developed so far. We say that f of x is ln x. We therefore say that the inverse function is e to the x because that is actually how ln is defined as the inverse of e to the x. And so we want to know, what is the derivative of e to the x? Well, that's asking for that's the derivative of f inverse. We plug everything into the formula, and that's 1 over, well, what's the derivative of f? That we just showed is 1 over x. So we have 1 over x, but we plug into it the inverse function, which we know is e to the x. So ultimately, by the inverse derivative law and what we know about logarithm, this is 1 over e to the x. Well, that's the same thing as just e to the x. So the derivative of e to the x is in fact e to the x. I should also point out, by the way, that when we have other bases, right, how do you deal with other bases other than e? Well, it is going to be different, and it's at least interesting to me to find out, like, why would it be different? Because so much of what we did here was just sort of generally using the properties of logarithms, and it didn't seem like I really used anything special about e at any point, except really pretty much right here, that this is the definition of e, and that we are plugging into ln. So if we didn't have a base of e, either in the logarithm or in the expression for e, then things would go slightly different. Now, that just says why things go different, but it doesn't really say how they go different. So let me just maybe type over here, because I didn't remember to make notes about this, so I'm just doing this off the top of my head. But let me just type over here exactly what would go different. Suppose that we want to know the derivative of 2 to the x, and so I write this. Well, here's a common, very easy trick when you get the hang of it anyway, which is that if I know how to do things with e, I can always force e into the picture, as I am wont to do so many times in the past in other sorts of ways and contexts, but this time I'm going to do it with e. So here I say that this is the same thing as e to the, what, ln of 2 to the x, because after all, e and ln are inverse functions and cancel each other out, and yet I'd still choose to do this because I want to work e into the picture because I know something about e. So I get to do this, and it seems like potentially a good idea. Now, I use the property of logarithms that exponents inside of a logarithm can become multiple factors outside, so that this is the same thing as e to the what? 2 ln x, basically, dropping as much parentheses and notation as I can permit. So this is just using the logarithm rule. And now I can use some exponential rules, right? Generic exponential rules, which is that this is the same thing as, actually, no. What I want to do at this point is chain rule. I now have a function and a function, and I know how to do all the derivatives. So the outer function is e to the x. The inner function is 2 ln x. I know that the derivative of the outer function is e to the x, right? That was what we just learned. And then the derivative of the inner function is in fact 2 over x, right? Because forget about the 2, it's just a constant factor. Take the derivative of ln x, you get 1 over x. So now it's 2 times 1 over x, which is 1 over x. Okay, applying chain rule, we get that this, the derivative, should be equal to the outer derivative plugging in the original inner function 2 ln x multiplied by, so on the outside multiplied by 2 over x, the derivative of the inner function. And at this point, I can kind of work backwards in exactly the same way that I worked forwards, and use my exponential and logarithm rules to sort of cancel e and ln, because it would be nice to be able to get them out of the picture if they were not there in the first place. So, okay, I take the 2 and put it back as an exponent inside of the logarithm, so I get that this is e to the ln of x squared times 2 over x. And at this point, what can I say? The e and the ln, sorry. I have flipped around the 2 and the x somehow at some point. Right, the x should have come out and the 2 stays in. That's a big deal. So correcting that real quick, this would just be ln2. I knew something was wrong. Okay. And so now plugging in the correct things, this is e to the derivative of the outer, plug in the original inner x ln2, and then multiply by the derivative of the inner, which is ln2, and then do my rearrangements backwards and say that this is e to the ln of 2 to the x, and still times ln2, and now e and ln cancel each other, so this is 2 to the x times ln2, and I am quite confident that that is the correct answer. So this is how you deal with a base that is not e. And in fact, this is a generic law that, if you had any other base, a to the x, right? We just did it with 2, but if you had a to the x and you want to find the derivative, it really always comes out to be a to the x. Not surprising, because it's kind of like e to the x, except that you get this little ugly factor of ln a sort of tagged on to the end. And we could do a similar trick if we have logarithms of any base other than e. I think maybe I'll try to build that up as an exercise in the coming exercise problems.